And if you're ready to go, then I'll
Yeah.
welcome Matt Baker from Georgia Tech, who will talk to us about matroids with coefficients and Lorentzian polynomials.
All right. So thank you for the invitation to speak here. I will be talking about joint work with Junha Mario Kummer and Oliver Lorscheid. And yeah, here's the plan. Wait, what's happening? Oh, there we go. Here's the plan. So Lorentzian polynomials, if you don't know, are some analytic gadgets introduced by Brändén and Ha and independently Anari, Ovescaron, and Vincent. They're intimately connected to log concavity questions. And kind of independently of that, for some number of years, I've been working with Nathan Buller, Oliver Lorscheid, and others to generalize the theory of matroids with coefficients, which was sort of pioneered in somewhat forgotten work of Dress and Wenzel. And what I want to talk about here is that turns out that there's an interesting connection between these two worlds, and I will try to explain this in some detail here. And it sort of came as a surprise. We weren't exactly looking for this, but it just kind of turned up, and it's pretty interesting. So what I need to do, though, to explain this is to talk about several different things. So first, I'll review matroids and their representations in a sort of classical sense, and I'll do that quite quickly, assuming that everyone here is familiar with this already, so this will be mostly to set notation. Then we'll need to generalize the notion of a field to something that Oliver and I call pastures. And I'll define what representations of matroids over pastures are. And then we'll switch to talking about Lorentzian polynomials, giving a quick background. And the sort of key connection comes from the fact that the support of a Lorentzian polynomial, the monomials where the coefficient is non-zero, is always a polymatroid. Now for this talk, for simplicity, I'll assume that all the polynomials that appear, all the monomials in their support are square free. So we actually get a matroid, not a polymatroid. This is just a technical thing that makes some of what I'll say easier. And then we need to relate the space of Lorentzian polynomials whose support is a given matroid M to representations of M, not over fields, but over these some funny pastures that I'll introduce. Okay, so that's the plan. All right, so let's start kind of slow with recalling the definition of matroid. So for my purposes, the sort of strong basis exchange axiom is the most natural one to look at. So a matroid is a finite set E together with a non-empty collection of subsets called bases, so that the following axiom is satisfied. If you have two bases and an element of one but not the other, then there's an element of the other one but not the first one, so that both of these exchanges are bases. So this looks stronger than the usual basis exchange axiom, but it turns out to be equivalent. Any two bases have the same cardinality called the rank of the matroid. It's some kind of analog of the dimension of a vector space. And a subset is called independent if it's contained in a basis. Of course, you can also axiomatize the independent sets instead of the bases, or the minimal dependent sets, which are called circuits, etc. But let's not go there. So the most common examples that one sees to get intuition, and maybe one of the original motivations for matroids, is the representable case. So this is where E indexes the columns of some matrix A with entries in a field K. And now the bases are the maximal linearly independent sets of columns. And one can check that this defines a matroid. And this is a kind of canonical example of a matroid. It's easy to see that the matroid you get actually only depends on the row space of the matrix, because if you do elementary row operations, you don't change the linear dependencies among the columns. So matroids of this form are called representable over the field K. And one of the goals of the talk will be to generalize the notion of matroid representations to things other than fields. And you might make some guesses as to how that might work from what I've said so far, but if you've never seen this before, what you're guessing is probably not what we do. It's important to note, though, that by a fairly recent, historically speaking, theorem of Peter Nelson, 100% of all matroids are not representable over any field. So this is something of a misleading special case, but nevertheless, much of the intuition for matroids comes from linear algebra. What I really want to focus on is the subspace, that the row space of that matrix A, which I'll call W, is a subspace of K to the N, and subspaces of a fixed vector space are parametrized by the Grassmannian. So hopefully you've seen the Grassmannian, but if not, here's an example. I mean, the general definition is a little bit unwieldy in terms of keeping track of minus signs and such, but we won't really worry about that. I think this example gives you the intuition you need. So suppose K is a field. Let's say we have a two-dimensional subspace W of a four-dimensional vector space K. Four-dimensional vector space. And it's sort of important for the combinatorial parts that we coordinatize the ambient space. So I really want to think of it as K to the 4, not an abstract four-dimensional vector space. And we can represent W as the row space of some matrix A. And then we look at the determinants of the 2x2 minors of this matrix, right? So if the columns, there's two rows, and if I pick two of the four columns, I and j, I get a determinant delta ij. So there's 6 of these numbers. And they're not independent. They satisfy a polynomial relation called the Plücker relation. And it looks like this in this case. Now, in general, there are many Plücker relations. If you have a R-dimensional subspace of an N-dimensional space, but this is a good example to keep in mind. And what you want to do is look at the Plücker coordinates, as they're called, these delta ij's, as defining a point of projective space, right? Because if you do that, then it turns out that this Plücker vector in P5 doesn't depend on the choice of the matrix A. It's an invariant of the original subspace, right? So if you multiply some row by a non-zero constant, you scale all of these determinants by the same constant, so you get the same element of projective space. And moreover, if you have a point of P5 which satisfies that Plücker relation from the previous slide, then there's a unique two-dimensional subspace W with those Plücker coordinates. So in a nutshell, that's the theory of the Grassmannian, that there's some polynomial equations that cut out the Plücker coordinates of subspaces. And this works for R-dimensional subspaces of an N-dimensional space. The Plücker equations you get define a projective variety called the Grassmannian, GRN. And in general, there's many homogeneous equations. They're all quadratic, called the Plücker equations. So it turns out, this is the first turning point of the talk. It turns out that matroids can be viewed as solutions to the Plücker equations as well, just like subspaces can. But in order to do that, we're forced to enlarge the notion or generalize the notion of field. So how are we going to do that? The idea is to relax the requirement in fields that addition arises from a binary operation. Okay, so I'll explain first with examples and then with axioms what I mean. So specifically, we're going to introduce an algebraic structure called the Krasner hyperfield, boldface K. And it'll have the property that solutions to the Plücker equations over the Krasner hyperfield are in one-to-one correspondence with matroids of rank R on an n-element set. So this analogy between subspaces and matroids is quite precise if we enlarge the set of algebraic objects that we are willing to look at equations over. Okay, so the thing is there's other hyperfields besides the Krasner hyperfield. I'll sort of define what that means later. And solutions to the Plücker equations over those are also interesting. But if we're going to go that far and allow, arbitrary hyperfields, then it turns out it's a good idea to go even further and generalize hyperfields to things that we call pastures. Okay, so I'm not going to focus on hyperfields per se, but on this even larger category. All right, so what is a field? Well, a field is an abelian group, right, under multiplication. Then you tack on some element that you call zero, which absorbs everything multiplicatively. And then you also have a binary operation plus, which satisfies some additional properties like commutativity, associativity, distributivity, etc. Right, so we want to generalize this. So we're still going to have an abelian group under multiplication. We'll still have an absorbing element called zero. And we still have some sort of additive structure, but it's not coming from a binary operation. So okay, so here's some examples to illustrate this relaxation of the notion of addition. So the Krasner hyperfield consists of 0 and 1. So the group is like the trivial group here, just the element 1 and with multiplication. Now you add on an element 0. And what are the additive relations? That's the interesting thing. So 0 plus x equals x for all x. That's a general axiom for pastures. But crucially, we have 1 plus 1 is 1, and 1 plus 1 is 0. So this is what I mean that addition doesn't come from a binary operation. You can't really define 1 plus 1, at least not as an element. If you like, you could say 1 plus 1 is the set consisting of both 0 and 1. And that's the traditional point of view on hyperfields, is that you allow addition to be multi-valued. But Oliver and I and Nathan and others have learned over the years that it's actually better not to define multi-valued like set-valued operations, but to simply have a list of equations that you declare are valid and then others that are invalid. So 1 plus 1 equals 1 is a valid identity, and 1 plus 1 equals 0 is also a valid identity in the Krasner hyperfield. And the way you should, right, so that's what I just said. And this looks weird.
Can I interrupt, Matt?
Yeah, sure.
I just want to make sure that I'm not supposed to think that equality is transitive then and that 1 is equal to 0.
Right, equality is not transitive here. Yeah, so
Thanks.
Yeah. In fact, I'm going to rewrite this in a different way soon, which makes that less confusing. Right. So because of Graham's question, it's a little bit better to write things differently, and I'll do that in a minute. But anyway, how should you think of this? If you think of 0 as a formal symbol meaning 0, and 1 as a formal symbol meaning non-zero, then this equation says that it's possible for two non-zero things to add up to something non-zero, and it's also possible for two non-zero things to add up to something that is 0. Those are both possibilities that are valid, and that's what this is encoding. So this is the arithmetic of zero versus non-zero. And if you think about matroids from the right point of view, that is what matroids are doing. For example, for a representable matroid, you don't really care exactly what the determinant of some minor of the matrix is. You only care if it's zero or non-zero. Okay, so that's why the Krasner hyperfield really is a natural thing to think about in the context of matroid theory, because it exactly is the algebraic structure that captures that intuition behind matroids. We're just worried about whether things are sort of linearly independent or linearly dependent, but we don't care about more quantitative values. All right, and now here's another example. This won't be so important in this talk, but in other contexts, it's very important. The regular partial field. So the regular partial field has three elements, 0, 1, and -1. And the multiplicative structure is exactly what you think. The additive relations, aside from the usual 0 plus x equals x, there's just sort of one other additive relation, which is that 1 plus -1 is 0. And -1 plus 1 is also 0 because it's commutative. But there's simply no relation of the form 1 plus 1 equals x. So again, we don't have a binary operation here, but for a different reason. So if you like, 1 plus 1 is now undefined instead of multi-valued. And it turns out we really want to allow both those possibilities, even simultaneously, for the same pasture. And that gives us a robust algebraic notion that we can work with. And anyway, how should you think of this? All right, ignore the F1 notation. I don't really want to get into the motivation for that. But the idea is that you're restricting arithmetic in the ring Z to a multiplicative subset, 0, 1, and -1. And since 1 plus 1 leaves that subset, it's simply undefined. All right, so what's the correct generalization of all of this? So it's very convenient to allow an involution x goes to -x so that we can introduce minus signs. For example, for the Plücker equations, it's very important that the signs kind of alternate. But in the Krasner hyperfield, this involution is just trivial. In other words, -1's the same as 1 in the Krasner hyperfield. And so to go back to Graham's question, instead of writing x plus y equals z, we're going to write that as x plus y plus -z is 0. That way, all our additive relations will be of the form a sum of three things is equal to 0. And then you're less tempted to apply some bogus transitivity law. It also makes the symmetry clearer because addition should be commutative, so to speak. I mean, there is no addition somehow, but if there was, it would be commutative here. So we're going to write a plus b plus c just to formalize this as a triple ABC, which is symmetric, so stable under permutations. And this will be called the null set of the pasture, the set of such triples. So here's the formal definition. Pasture is a multiplicative monoid with 0, such that everything except for 0 forms a Billing group under multiplication. You have an involution called negation that fixes 0. And you have a set of triples, this null set, which is symmetric under permutations. So that's kind of like commutativity. You have a weak version of distributivity, which is that if you take a triple of things that's supposed to add up to 0 and you multiply it by scalar, it should still add up to 0. Okay, so null sets are invariant under multiplication by scalars. And then this involution should have the property that sort of 0 plus x plus y is 0 if and only if y equals -x. It's a little harder to motivate why we want that axiom, but it turns out to be very useful. And that's it. Those are all the axioms for a pasture. So it's actually very simple. There's no associativity property, for example. And no fancier version of distributivity here. So a homomorphism of pastures then is a multiplicative map that takes 0 to 0, 1 and 1, and takes null expressions to null expressions. You should also demand that it preserves negation, but that's automatic from axiom 3 here, if you think about it. So if you use this hypersum notation here to denote the set of all z's for which x plus y minus z is null, then field means exactly that this hyperoperation is actually an associative binary operation. So fields are the case where this construction, does correspond to an honest binary operation. If this operation always gives you a non-empty set and there's some suitable associativity, then that's what a hyperfield is. And if you have at most one z for which x plus y minus z is 0 for every x and y, and you satisfy some kind of subtle associative law that I'm not going to talk about, then you call P a partial field. But we won't really focus on these special cases, and we won't care about associativity. We'll just use this notion of pasture. So they generalize both hyperfields and partial fields. All right, one of the main players for this talk is the tropical hyperfield. This is, depending on the day, my favorite hyperfield of all. The tropical hyperfield, which in this talk I'll call T0, as a multiplicative monoid is the non-negative reals. And the additive relations all look like x plus y equals 0, where x is less than or equal to y. In other words, x plus y plus z is 0 in the tropical hyperfield if and only if the maximum is achieved at least twice. And this should remind you of some conditions in tropical geometry. And indeed, you can really do many things in tropical geometry more naturally with this structure than with the usual semifield structure. Now, in tropical geometry, it's traditional to take logarithms so that instead of having multiplication be multiplication, multiplication becomes addition. But I'm not going to do that because the notation gets very confusing. And it's actually more natural for what I want to say here to consider things in this multiplicative framework. So it's kind of the same deal as absolute values versus valuations. They kind of encode the same information, one multiplicatively and one additively. Now, another star for this talk is the triangle hyperfield, which was introduced by Viro decades ago, but it's getting a revival here. It's again, as a multiplicative monoid, it's the same as the tropical guy. It's just the non-negative reals. But now, what are the additive relations? So you say that 3 non-negative real numbers add up to 0 in this structure when they satisfy the triangle inequality. So they form the side lengths of a Euclidean triangle. And we allow degenerate triangles, where, say, 2 of the lengths coincide and the other one is 0 or something like that. And more generally, there's a whole family of hyperfields that we call TP, all with the same underlying monoid. But the additive relations, now you raise x, y, and z to the 1 over pth power, and you want those to form the side length of a triangle. And the reason for doing this is that you can view the tropical hyperfield T0 as a limit of these triangular hyperfields. So in some sense that I won't make precise here, the TPs converge to T0. Just think about the fact that if x x to a very large power, y to that power, and z to that same large power form the side lengths of a triangle for arbitrarily large powers. The only way this can actually happen is if the maximum is achieved twice. Okay, so now it's time to put these algebraic structures to work and tell you how to represent matroids over pastures. Okay, so we start with a matroid M of rank R on a finite set E. P is a pasture. And we want to define a representation of M over P. Now, it's not really a good idea to define it as a matrix per se, because you can't really define determinants of matrices in this generality because we don't have the notion of addition. So what we really want in the end of the day are determinants of matrices, not matrices themselves. So we simply hardwire it. We throw out the matrix and we record the algebraic properties of determinants. So the first thing we want is that in order to represent this matroid, this determinant-like function delta should be non-zero exactly when our things form a basis. Okay. Second, it should behave like a determinant does under permutations. And then crucially, delta should satisfy the same algebraic relations that determinants do, which are these Plücker relations. And this is sort of the general form of the so-called three-term Plücker relations. It looks very much like what I wrote before, but now we have a larger ground set, and so we have to, allow arbitrary j's here together with 4 additional elements that we throw in and out the way we did before. By the way, if you contract this set J, then you get like a U24 minor of your matroid, and then you really just have the G24 Plücker relation that we had before here. So these three-term Plücker relations correspond to U24 minors in some way. But anyway, you might ask, why not use all Plücker relations? Because there are also 4-term Plücker relations, etc. But this is kind of a technical thing I don't want to get into in this talk. There's a notion that Bowler and I have of weak versus strong matroids. And yeah, it's a little bit annoying. And luckily for this talk, we can gloss over this. So for the experts, I'm only talking about weak representations in this talk. So that's what a representation is now. And actually, I just lied. A representation is actually an equivalence class of such functions. This is because if you remember, we were looking at the Plücker equations in projective space, not affine space. So we need to identify determinant-like functions that are scalar multiples of each other. And now we really have like Plücker vectors. So the set of all representations of M over P, I'll denote by R sub M of P. Okay. Oh, and I think I'll say this later, but it's essentially the usual notion when P is a field. I think I have a remark about this later. One more thing. It's useful to introduce rescaling classes, or in matroid theory, classically, this is called like projective equivalence of representations. I just don't like the word projective in this context because it's potentially confusing, since we're also looking at the Plücker vectors in projective space, and it's kind of a different meaning. So we say that delta and delta prime are rescaling equivalent if, well, you can read this. It's a more flexible notion of equivalence that makes more thing equivalent. But the intuition here is simply on the level of matrices, what we're doing is saying, besides elementary row operations, there's another thing that doesn't change the matroid, which is rescaling individual columns. Right? So if I multiply some column of a matrix by something non-zero, it obviously doesn't change which columns are linearly independent. And if you allow independent scalings for each column, it has this effect that I'm writing down on the determinants. And those of you that are familiar with matroid representation theory know that this is a good thing to do. So I'll use R underscore to denote rescaling classes of representations. These are just a little simpler, a little nicer. All right, so this is what I mentioned before, that if K is a field, then a K representation in this new sense here automatically comes from a matrix representation. So even though we threw the matrices away and only considered determinant-like functions, the theory of the Grassmannian shows that there is actually a subspace, or if you like, a matrix, automatically in the background once you satisfy these Plücker equations. So over fields, we're doing the same thing as people do classically. But now we can represent matroids that aren't representable over fields, because every matroid is representable over the Krasner hyperfield, in fact, in a unique way, right? Where the determinant function is 1 if it's a basis and 0 if it's a non-basis. And the fact that that satisfies the Plücker equations is precisely the strong basis exchange axiom that I wrote down earlier. So we get that every matroid is now representable. And this F1 thing I introduced before, that's related to regular matroids. So being representable over that F1 is the same thing as being a regular matroid. Now, in general, a regular matroid can have many different representations, but they're all rescaling equivalent. So this is the sort of well-known fact that all regular matroids are uniquely representable if you allow projective equivalence. And one of the stars of this talk will be valuated matroids. These are matroids together with a representation over the tropical hyperfield. And these are related to tropical geometry in a very nice way, but I won't get into that. Instead, I'll just give some examples of how you can construct valuated matroids. So to get a valuated matroid of rank 2, I mean, let's assume it's a simple matroid, so we have just U2n. Then a valuation on M, meaning a representation over the tropical hyperfield, is the same thing as a phylogenetic tree with n leaves. So what does that mean? It's like a tree where each edge is given a length, and there's n leaf nodes of the tree. And the logarithm of the determinant function here is just the tree distance. So this is a very nice, beautiful classical fact interpreted in the language that I'm using here. By the way, technically speaking, to make this true, you have to allow negative lengths on your trees. But this won't concern us.
And Matt, are your phylogenetic trees have the property that they're equidistanced? Like there's a root
no,
no?
not necessarily. They're all equivalent under rescaling to something equidistant. That's a classical fact. So yeah, I mean, if you like, you could assume that, but no, that's not part of the definition.
Okay, sure.
Okay, so yeah, every value, every T0 representation of U2n comes from some tree. And rescaling equivalence in this context is like rescaling the lengths of the leaf edges. And so if I just make one leaf longer, that's like rescaling a column of the matrix, of the distance matrix. Okay. So now, where does some of the power of this theory come from? I mean, so far this has all been descriptive, but where this actually becomes useful is that we have these universal gadgets, which you simply don't have in any classical setting. Namely, if you fix the matroid M, you can consider the representations of M as a functor, where you input a pasture P and you output the set of representations over P. And in fancy language, that functor is representable. And the pasture that represent it, we call the universal pasture of M. And if your category theory is rusty, that means that there's a natural isomorphism between hom from the universal pasture into something with this representation functor. Maybe if your category theory is rusty, that didn't help. But anyway, that's what it means. But it means that you can, for example, very concretely, if you want to see whether a matroid's representable, even over a field K, you simply have to compute whether there's a homomorphism from the universal pasture into K or not. So in principle, and there's an algorithm to compute this universal pasture. In fact, it's been implemented in Macaulay 2. You can just ask a computer what PM is, and then you can calculate homomorphism. So in principle, this is an algorithm to determine representability of matroids. Of course, the catch is that these things get really complicated quite quickly, and so the computations become somewhat intractable, but that's life. There's also the foundation of M, which represents the rescaling class functor, and it's a little bit simpler to compute and work with. All right, just for the record, I don't think I'll really need these things later, but the universal pasture of M and its dual matroid are canonically isomorphic. Same for foundation. If you have a minor n of a matroid M, there's a natural map from the foundation of n to the foundation of M. Technically, you need an embedded minor, namely, you need to keep track of what you deleted and what you contracted, because the homomorphism depends on that data. And the multiplicative group of, say, the universal pasture is something that was already known. It's called the Tut group, which was introduced by Dress and Wenzel. So if you've seen the Tut group or the inner Tut group and you wondered what they were, this is what they are. The advantage of our formulation is that there's more structure now. It's not just a multiplicative group. It also has an additive structure to it. And we can characterize these things by a universal property, whereas for Dress and Wenzel, the Tut group was simply defined by generators and relations in like 3 or 4 or 5 different ways. But you couldn't really answer the question, what is the group, in like one sentence without giving a explicit description of it. But now we can. So it's the usual philosophy in sort of abstract algebra or category theory that it's kind of better to define things by universal properties and then give concrete constructions of those things rather than defining stuff by explicit constructions. Okay, and now we're going to take like an apparent detour into Lorentzian polynomials. Any questions before I get into the final part of the talk? All right. Seeing none, I will move on. So what are the goals of the theory of Lorentzian polynomials? Is to give new techniques to prove that certain sequences are log concave, meaning, AK squared is at least the product of the previous term and the next term for all K. So for example, these were famously used to prove Mason's conjecture. If M is a matroid and IK of M is the number of independent sets of size K, then this sequence is log concave. And there are many theorems like this. There's also a stronger version of Mason's conjecture, but anyway, I'm just illustrating how these things arise in practice. And so what is a Lorentzian polynomial? As I mentioned earlier, I'm going to restrict to square-free support polynomials. The technical word is multi-affine. Just for simplicity, our paper's written in complete generality. So HRn for me will be the square-free homogeneous polynomials of degree r in n variables with non-negative real coefficients. So Lorentzian polynomials are such things with an extra property, namely that the logarithm of f is concave on the positive orthant. So of course that just means that f satisfies some inequalities like this. Okay, so I just want to stress that the definition is analytic in nature, right? It's some condition about logarithm being concave, which you can formulate in terms of second derivatives, if you like. So speaking of second derivatives, you'll probably recall from calculus that the Hessian of f is a symmetric matrix given by the second partial derivatives. And one theorem is that a polynomial is Lorentzian if and only if its Hessian has exactly one positive eigenvalue at every point of the positive orthant. Okay, so now we can also describe Lorentzian polynomials in terms of linear algebra. So there's sort of a calculus description and a linear algebra description. And now the claim is that secretly there's also matroids lying around, even though we haven't said anything combinatorial yet. Oh yeah, let me give you an actual example. So the elementary symmetric polynomials are always Lorentzian. So for example, this elementary symmetric polynomial of degree 3 in 4 variables is a Lorentzian polynomial. So the surprising theorem that kind of links this to combinatorics is that if you look at the support of a Lorentzian polynomial, it's always a matroid. Specifically, it's the set of bases. I mean, you can identify monomials with subsets in the square-free case. And I want to say that the monomials that appear correspond to the bases of a matroid. And even more surprising in some sense is that every matroid arises from this construction. So if you know about stable polynomials, those are always Lorentzian, but not every matroid is the support of a stable polynomial. So that's why Lorentzian polynomials are sort of better in a concrete sense than stable polynomials. So I'll let L sub m denote the space of all Lorentzian polynomials with support equal to a given matroid M. And for various reasons, I actually want to mod out by the action of the positive reals by scalar multiplication. So sort of looking at Lorentzian polynomials in like projective space rather than affine space, partly because I want to compare them to matroids, but also because the space is a little more interesting in this case. So a key theorem of Brändén and He actually uses the matroid support to do something nice. Namely, the following are equivalent: f is Lorentzian, or the support is a matroid, and every partial derivative which is quadratic, right? So you differentiate r minus 2 times if r is the degree, till you get down to a homogeneous quadratic form. Its Hessian is just a constant matrix, and I want that to have at most one positive eigenvalue. But you see, this is kind of better than the previous condition because this is a finite number of things to check. Whereas before I had to check that the Hessian had one positive eigenvalue for every point in the positive orthant. But now I'm only looking at finitely many quadratic derivatives, and their Hessians are constant. So there's only a finite number of things to check here. This is actually a fairly deep and difficult theorem. It should also remind you of the fact, well, somehow of representations of matroids where it was kind of important. I suppose I hit it earlier, but it was important for my definition of matroid representations that we actually start with something where the support is already a matroid. Otherwise, the definition of satisfying three-term Plucker relations doesn't have good properties. All right, anyway, here's the connection now to between these two parts of my talk. The first connection is this theorem. For every matroid, the space of Lorentzian polynomials with support M is a topological manifold with boundary. This is already not obvious, but in particular has a well-defined dimension. And the dimension is the rank of the Tut group of M. So the rank of the multiplicative group of the universal pasture. And this was sort of a surprising computation, I think. So yeah, if you like, that's another answer to what is the Tut group. Well, at least the rank of it, it's the dimension of the space of Lorentzian polynomials. Okay, now what can we do with this connection? All right, so I'm going to say more about the connection, but this is the first interesting connection between the two worlds. A theorem we were able to prove using by looking at things in this way is if you now take the closure of L sub M, and there's two kinds of projectivizations sort of going on here, or two kinds of closures. So anyway, you make this space of Lorentzian polynomials compact in some natural way. And Brändén asked if this is always a closed ball. And in kind of many examples, he could prove that it was. And if you use a computer and you try to calculate this, you'll see that it seems to be true. But we actually found a counterexample. So there exists a matroid M such that the compactified space of Lorentzian polynomials has Euler characteristic different from that of a ball. So I think the interesting thing is how we were able to compute the Euler characteristic, because this looks like it's really hard to compute the space of Lorentzian polynomials as a kind of manifold and work with it on a computer. So what we did is we actually, well, you'll see, we proved a structure theorem about such things. Anyway, just as a sort of side note, but I think it's very interesting, the matroid we found, and I think we only have one counterexample right now, it's a very interesting matroid. It's somehow like a combinatorial analog of a moduli space of elliptic curves. So these things have recently been studied by Borisov and Rouleau. For each n, there's a matroid Tn, which is like ridiculously simple to define. A three-element subset is a non-basis if and only if the sum of the elements is 0 mod n. But it turns out that representations of this over the complex numbers correspond to elliptic curves together with a point of order n. So anyway, what we proved for this particular matroid T11 is that its Euler characteristic is actually 11, not 1. And the fact that it's 11 and n is also 11 here is probably not a coincidence, but we don't have a general theorem that says that. So this is an open problem to understand better. Anyway, the way we actually compute the Euler characteristic is to find a different compactification that is a ball. Namely, so there is always some way to compactify the space of Lorentzian polynomials that gives you a ball. And what you do is you glue in a copy of the boundary of a ball of the right dimension where you take away the valuated matroids with support M. So why does this show up, the valuated matroids with support M? Well, they're related to Lorentzian polynomials. So Brändén and Ha showed that valuated matroids give rise to Lorentzian polynomials. I mean, literally just write down the coefficients are kind of these Plucker functions, Plucker coordinates, the coefficients of your polynomial. And they show that this is Lorentzian. And it's related, by the way, to the phylogenetic tree stuff. The proof eventually reduces to rank 2 and looks at eigenvalues of distance matrices of phylogenetic trees, which have Lorentzian signature. Okay, so the rest of the talk is motivated by this picture. The left is exponential coordinates. The right is more beautiful after we take logarithms of everything. So this is for U24, which is sort of the most important non-trivial case to understand. And on the right-hand side, the green is the space of Lorentzian polynomials, or you take pointwise logarithms of the coefficients. And then the tropical line in dark green is the Dressian of U24, namely the space of valuated matroids. And by the way, just since I mentioned it earlier, I mean, why do you get 3 rays in the Dressian of U24? It's because there are 3 possible types of phylogenetic trees with 4 leaves. Well, there's a degenerate kind, which is just a star, but otherwise, a phylogenetic tree with 4 leaves looks like a quartet. You've got 2 pairs of leaves joined by a segment. And there's 3 ways of partitioning your 4 elements into 2 blocks of 2. And so that it somehow explains this picture, at least the Dressian part. But we were very intrigued by this picture. It looks like Lorentzian polynomials not only contain the Dressian, but the shape is kind of governed by the Dressian. And that's what that theorem about filling in with balls is trying to say, that the Dressian actually determines the topology of the space of Lorentzian polynomials. In this picture, you can see that the non-compactness comes from the 3 missing points out at infinity, which are determined by the directions of the rays of the Dressian. So that's the idea of our general theorem. Also, now we had the idea that one should look at not just Q equals 0, but other Qs. And something very surprising happens for U24. Namely, it turns out that space of Lorentzian polynomials is on the nose, the representations of U24 over the triangular hyperfield T2. This has to do with taking square roots, like when the square roots of 3 numbers form the side lengths of a Euclidean triangle. That turns out to encode like 4x4 matrices with Lorentzian signature. So you might ask, what the hell? Where does that come from? And there's actually a super elementary way to see this, but it's still a little mysterious to me. Namely, I mean, once you see this connection, you just are motivated to write down the following calculation, that there's a Euclidean triangle with side lengths A, B, and C if and only if this quartic equation is satisfied, or quartic inequality. So this is a fun thing to try to prove if you want. But as a hint, there's actually a geometric meaning to this. If you look at Heron's formula for the area of a triangle, the thing inside the square root, if you expand it out, is exactly this quantity that's supposed to be non-negative. Okay, so now let's generalize this to arbitrary matroids, and then that's the end of my talk. So in general, what happens? Lorentzian is always contained in the space of T2 representations. And for any Q greater than 0, the space of representations of M over TQ is homeomorphic to the space of Lorentzian polynomials. So really where the dimension calculation came from, this inner Tut group showing up, is that it's pretty easy to see that the dimension of the space of representations of a matroid over TQ, where Q is positive, is exactly the rank of the Tut group. And that space turns out to be homeomorphic to the Lorentzians. And so again, in this previous picture, you can sort of see that well, here it was just equal to Rm of T2. In general, it's just a homeomorphism. So anyway, Lorentzians are, for example, homeomorphic to representations over T1. And using this, we can actually deduce things about spaces of Lorentzian polynomials. So here's a sample theorem. If M's a binary matroid, then the space of Lorentzian polynomials with support M is just a product of finitely many half-open intervals. And if M is ternary, namely representable over the field of three elements, the Lorentzian space looks like a product of finitely many half-open intervals and then disks with 3 points removed, like that U24 example that I showed. And in general, it's a little complicated, but we can say something interesting. For any matroid, Lorentzian polynomial space is an inverse limit of topological spaces that either look like half-open intervals, disks with 3 points removed, or a five-dimensional ball with a copy of the Peterson graph removed from the boundary. That already happens for U25. Lorentzians look like that last case. But that's all the possibilities. And this is proved by classifying representations over T1 and transferring that by our homeomorphism theorem. I have no clue how you could try to prove that directly using the definition of Lorentzian polynomials. Seems impossible to me. But we can also go the other direction. We can deduce things, for example, about valuated matroids from knowing things about Lorentzian polynomials. So if you look at the Dressian, which is all valuated matroids of rank D on n elements, Brändén showed that the corresponding space of all Lorentzian polynomials is homeomorphic to a closed ball by a very kind of complicated, intricate argument. He proved that. And so as a consequence, we don't actually obtain that the Dressian is a ball because we don't know that these homeomorphisms glue properly. We do at least get that the Euler characteristic of the Dressian is 1. And this seems to be a new theorem about spaces of valuated matroids, which we deduce from knowing something about Lorentzian polynomials using analytic methods. And so we don't know how to prove this without this detour into the theory of Lorentzian polynomials. And I think I will skip the last slide because I'm out of time, and I will just take questions now. So thank you very much.
Thanks, Matt. Turn it over to the audience for some questions. If you want to just jump in, that's probably okay.
So it's kind of a
You got a
question.
question?
Yeah, okay. So, okay, so this is a little vague, but I guess if I understood correctly, the sort of main like connection between the algebraic setup you had earlier and these Lorentzian polynomials was about the support of these polynomials, and then you discussed these things related to like, oh, are these topologically related to like balls and so on, at least after compactification. I know this is like a lot of the actual results are specific to this Lorentzian polynomial context, but I was wondering if there's any other use of the setup you had earlier to like sort of a lot of examples in combinatorics where things are topologically equivalent to like something related to spheres or wedges or like when this does not happen. Like let's we have some complex and then you specialize to say like independence, like some complex associated to a matrix. I don't know.
Yeah, I mean, I don't, what I've said here is somewhat specific to
Uh-huh.
this Lorentzian setup, but
Right.
yeah, in principle, I mean, I've been working with some collaborators and students on thinking more about Menyev's universality
Oh,
theorem
okay,
from
cool.
this point of view. And I think
Uh-huh.
we can say, hopefully, at some point, some new things from the point of view of foundations, where you're trying to show that that spaces